Okay, welcome everybody to the penultimate session. I'm still trying to find out where to hold the microphone. We have 3 speakers in the session, and I will use a rattle to make them aware that it's 3 minutes before the end, and then perhaps questions. 1 rattle, wrap it up. 2 rattles, you should really stop. 3 rattles, and we make a conga line out of the room. I will lead the conga line. Good. First speaker is Fasana on assessing the influence of the MOP on spatial models for aerial disease data in Queensland, Australia. Please.
Thanks, David. Okay, hello everyone. This is Fasana. I recently joined Murdoch University as a lecturer in statistics, and today I'm going to talk about one of my ongoing projects with my previous workplace, which is QT Center for Data Science. That's my project team. We have collaborators from Cancer Council Queensland and few people from QT Center for Data Science and myself from Murdoch. And this is funded by a second bind grant from QT Center for Data Science, which is aimed for early and mid-career researchers. So today I'm going to talk about spatial data and specifically aerial spatial data, as you have guessed from my title. So we have looked quite a few different talks on spatial data this conference, even in this morning. But today I'm going to talk about the aggregated spatial data. So when you have some information on individual level in specific regions, if you add those up for specific small area boundaries, that's what gives you the aerial spatial data. And here is an example in this slide. So you can see this is a map that has been extracted from Australian Cancer Atlas. And these different segments you can see are the statistical area level 2. That is an ASGS boundary set up by ABS. So Australia is, the whole Australia is comprised of more than 2,000 SA2 levels. And in this plot, we can see 2,148 SA2s in particular. The other ones have 0 population, so has been excluded. And the different colors here are showing how the incidence of liver cancer varies in specific regions. So when you see the neutral color, that means a specific region has the similar incidence as Australian average. The cooler color are for lower than Australian average, and the hotter color are higher than Australian average. And you can see the patterns and clusters going on in this map. So aggregated spatial data for disease is very useful for analyzing and modeling because of so many reasons. Here I just summarized few. So first of all, individual disease data is sensitive, and there are ethical issues and identifiable issues to use those in modeling. That's why most of the times in disease data, if you are interested in more knowing the spatial pattern across any geographic region, you aggregate it and then model it. It gives you nice disease maps that can tell you different stories about diseases, different patterns you can see. It can also help you to find out hotspots, if there is any clusters or disparities. So all these reasons make aerial spatial data and modeling of aerial spatial data in disease mapping very popular. But whenever I go and present some spatial aerial modeling to any audience, the most frequent question I would say is, how does your inference change if you change the boundary level of aggregation? And it could change. And that's the topic I'm interested to talk about today. It's called modifiable aerial unit problem, or MOP. So MOP is the problem that happens if you change the aggregation boundary. For example, if you're aggregating lung cancer incidence information for mesh block level, you'll have a different data. If you aggregate up for SA1 level, you'll have different number of SA1 and different result. So on, if you aggregate up to SA2, SA3, SA4, it changes. So that could have an effect or impact on the model estimates that you can see. So in the literature, people have been studying about MOP, and they have been showing how MOP can cause issues in your inference and how it can be tackled. And in the literature, it has been said that investigation of MOP is very dependent on specific geographies, and it also depends on specific data that you are using. And in the literature, there is a gap that there is not much study that has talked about MOP in the context of Australian geography for cancer incidence data. So that's one of the main reasons for doing this analysis or research. We want to find out how MOB influences the analysis of cancer data in different regions of Australia if we use different boundary levels. So we are using 4 types of different boundary levels that are given by ASGS boundaries. And we would like to see how this changes the model inference and how and what type of data or what level of data you should use for your modeling if you have more than one boundary levels data available to you. So those are all objectives in our mind, and we started our analysis with set of simulated data. So this is simulated lung cancer data that has been simulated by Cancer Council Queensland. It has captured the original patterns and rates underlying the disease in whole Australia, but just to be cautious about the ethical issues, we are not using the real, but the simulated data. And here in this map, we can see how different geographics are changing the patterns. So in the first plot, you could see the SA1 level data. So there are so many small areas because it's a smaller boundary levels, and different colors are showing you different numbers. Numbers started from 0 up to 15. On the second plot, you could see it's SA2 level, so little less number of areas now and more aggregation happening. And we are only looking at Queensland here because of the computational constraints for this study. So that's why we are looking at Queensland's map only. Here you could see more aggregation happening. So the first one is giving you SA3. So the numbers go even higher because now the boundaries are higher. And then you could see what's happening in SA4. You have very lower number of SA4s. That's why in each of the areas, the number of cancer incidents or lung cancer incidents is high. So this descriptive table just gives us an overview of the exploratory data analysis that we just saw. So in whole of Queensland, you have over 67,000 mesh blocks. So mesh block is the lowest level of small area aggregation by ABS. So after you mesh block, you could get SA1 level data. Then if you aggregate up, there are SA2, SA3, and SA4. These are the different number of areas, and you could see the descriptives for lung cancer simulated data. So what we wanted to do with this data is we wanted to fit the same model for different aggregation level to see how inference changes when you are using SA1 level data versus SA2 level, 3 level, or 4 level. So the model we are using for this research is the very well-known BYM model. So that's a model for disease mapping that has been here from 1990s. It uses conditional autoregressive priors for our spatial random effect in the model. So since we are modeling cancer incidence, that is the number of cancer cases diagnosed in each of the small areas, aggregated form, it is a Poisson distribution. So the first layer of the model is Y, that is your observed lung cancer incidence coming from a Poisson. And then the rate of the Poisson distribution could then be modeled in the next hierarchy. So this is a Bayesian hierarchical model with spatial random effect terms. So the last term in equation 1, which is psi I, it is the spatial random effect that is capturing the neighborhood structure of I, the spatial area, by using BYM car prior. And X could be any covariate. So for now, for this simplicity of this analysis, we are using the social economic advantage and disadvantage scores that is called SEIFA quintiles by ABS, to see how different socioeconomic areas have different incidences of lung cancer. And we are going to fit this same model for mesh SA1, SA2, SA3, and SA4 level data. And we would see what different types of estimates we could get. So this is just a summary table for one of the model. So we used one covariate SEIFA quintiles, which had 5 categories. And the category 1, which is most disadvantaged, is the reference category. And you could see the different betas. So we are not very interested now in looking at the influence. Rather, we want to see what are the differences in the inference for different area level we are using. So if you just look at the confidence intervals or credible intervals in this case, because these are from posterior distributions, you would see for SA1 and SA2 level, your estimates of the regression coefficients are all significant. And for the SA1 level, you have narrower credible intervals because you have so many areas. So statistically, it's kind of a sample size thing going on. In SA2, you have a little wider confidence in a credible interval, but still the effects you are getting are significant. But when you aggregate up to larger boundary levels, such as SA3 and SA4, you lose the capacity to identify the significant effects because you have aggregated to larger boundary and you have lost the details to be able to estimate the impact significantly. So that's what we can see from these tables. So these are the Moran psi value. We wanted to see what is the spatial autocorrelation or degree of spatial autocorrelation in the observed data for a specific level, also in the model residuals. So if we only look at the first two columns, these are giving us the spatial autocorrelation that is in the small area level data. So for SA1 and SA2 level, you could see the p-value is very small. That is, when you have SA1 and SA2 level areal spatial data, they are highly spatially autocorrelated. They are depending what their neighbors are, and that should be considered when you model them. But when you move on to larger aggregation boundaries, such as SA3 and SA4, the degree of spatial autocorrelation are no longer significant. So by looking at all those and also by looking at computational complexity, convergence and everything, which for time constraint I did not include in the slides, we just tried to see what we are gaining in a specific aggregate level and what are we losing. So as you can see, for mesh block level, because you have so many mesh blocks, the inference you get is highly precise. When you get on to SA1, it is still precise. SA2 is still precise, but you lost the precision and you get the more credible interval width when you get to SA3 and SA4 level. One disadvantage of having a smaller aggregate level is the computational cost. For mesh block and SA1 level, you cannot use your computer to run the models. You need to have high performance computing system. So those are some issues we have found out. So in conclusion, we just wanted to say that though it's statistically more efficient if you use a smaller boundary, but to consider for the computational cost, you should settle for a boundary level that gives you precise result, but not too computational costly, which comes to the SA2 levels. So as a modeler, if you want to model disease data, go for SA2 level, and that will give you precise results. And these are some references I used. And the last thing is we also made a Shiny app where you can go and play with different levels and see how the data changes. Thank you all.
Thank you, Prasanna. Any questions here? Oh, I should put this down now. Not that the people form a conga line. Are you fitting the models using MCMC or INLA?
And MCMC.
MCMC.
Car-based.
Because by BYM can be fitted with INLA, and that's usually faster than.
Yeah.
It was our experience. There are a lot of interesting problems in that area. Any other questions? I think these are. Is the ideal zoning different when you compare urban areas versus rural ones?
For this model, I haven't included remoteness, but yeah, we are fitting another models where our covariate is remoteness of categories, which is our major cities, regional and rural, and we are doing that, but unfortunately not in the slide.
I should probably also mention there's this whole field of small area estimation, but SA stands for statistical areas,
yes, not
small areas. But with the first picture, I always thought like, yeah, we have the largest small areas here in West Australia. We beat the rest. But statistical areas. My small areas are bigger than yours. Any final question, comment? No? Then thanks again, Prasanna, for the very interesting talk. And some of my co-authors were once amazed that I wrote in a sentence, solving this by back elimination is straightforward, that I got backwards and straightforward within 4 words together. Our next speaker, that key actually gets long and short right next to each other. And he's talking to us about predicting marimba stickings using long short-term neural networks, once Xixing has wired them up.
Cool.
Ready? Ready? Go.
All right. Thank you, Bowen, and thank you to the ECSS for running and having us here. I'd like to also extend Conga Lion time. I'd like to extend our respect to the Whadjuk Noongar people, traditional custodians of this land, and it's really a privilege to be able to meet on Whadjuk Budja. So I think a couple of immediate questions come up when we see this kind of topic. 1, what's a marimba? 2, why is it sticky? And 3, why should I care? And I think I'd like to answer the last bit first in this case, because this is within a field of music on a relatively niche set of instruments, and it's a field that doesn't really see very much application contemporarily in a sense of statistical processes. And I guess of all fields, it's on the less statistically literate side in the general sense, not to say that there's no research being done in that space, of course. So some of the problems that I'd like to present today come not so much from perhaps the models of the results, but from the approaches taken to try to quantify and to try to put into statistical terms some aspects of this field of music, which are traditionally quite difficult to do to varying degrees of success. So without further ado, let's dive into it. A marimba is a musical instrument, which, if you know anything what a xylophone is, a whole bunch of wooden bars which are tuned. Think a xylophone, but it's about 3 meters long, about 1 meter deep, about 1 meter high, and it barely fits into a sedan when you break it down. So it's a bit of a beast to move around, and something that comes along with an instrument of that size is a physicality that comes with it. It's a very dynamic instrument to play. When playing a marimba, typically performers will have 4 sticks, 2 in each hand, and they'll be playing using sticks 1, 2, 3, and 4. And if you're navigating a 3 meter wide instrument with these sticks in your hand, it's quite a full body experience. The challenge of this is, okay, so I've got a whole bunch of sticks in my hand and I've got a whole bunch of notes to play. How do we know which stick to play which note to avoid our hands tangling into each other and to avoid everything kind of going haywire? And that's where stickings come in. We allocate a certain number to each note, and that helps us decide the best way to play a note. But what do we mean when we say a best way? Because there's many different schools of thought. Some people might say, okay, maybe we want to reduce the motion we have to do. Yeah, we want to try and make it as easy as possible. But other schools of thought would suggest that if you play it in a certain way that minimizes motion, you may not get the best musical expression or the best musicality out of it. And these enter some really difficult discussions on how to try to optimize this problem, which takes it from a relatively straightforward kind of cost minimization problem to something that can be a lot more challenging to solve. Just as an example, and I won't assume everyone reads music here, but if we observe this circled note is a 4, implies using stick 4. If we change the context of the music, so it's the same notes, but now in a longer passage, the best sticking, or perhaps the optimal sticking, might change to, in this case, a 2, or maybe back to a 4. So it really depends on what comes before, what comes after. And we see in this data long-term time dependencies across the time series data. Additionally, this is not a process that can be easily translated up and down an instrument. So we've got these wooden bars laid out in a piano-like pattern, which is a little bit irregular. And if we take the same music and move it just a couple of notes either side, something that works really well in one key, when we change the key, suddenly tangles your hands up. And I should mention that whilst it's not, a world-shattering problem that someone's hands get tangled up on stage, long-term exposure to poorly stuck, bad stickings in a piece of music and leading to bad practice can result in performance injury. And that's something that we obviously try to avoid. So I think some of the interesting aspects of this research are coming to how do we encode this kind of data in a way that will be most efficiently machine read. And there's numerous ways that we can encode this data, of which I'm showing two here. Perhaps the natural, the naive approach is something that's called one-hot encoding, where we say, okay, there's 61 keys and we play a note for a certain duration. We're simplifying a little bit here. Let's just put a 1 as an input for the vector that's 62 dimensions wide, and we'll just use 62-dimensional vectors to represent the input space. That's totally fine. That works. We call that, in this case, pitch vector encoding. Another method used by researchers Nakamura et al. In piano fingerings, which is a similar related topic, instead said, okay, if we're going to move from one note to the next, rather than encoding the notes themselves, what if we map these out using different axes? And we then track how the axes change as we move from note to note. And this is another valid approach. It's a much simpler approach in terms of the data stored in it, but it also loses some other information. And I should also mention that the first approach in this case can handle playing multiple notes at the same time. The second approach is a little bit harder to do so, and then we have to consider some ways that we can work around that. In this case, setting rhythmic durations to like 0 seconds. So these are a couple of the encoding methods that we took on board when trying to design this model. When it comes to actually choosing a model though, we have to also bring in a whole bunch of other considerations. So in this case, we're looking at time series data, and we're looking at time series data with long-term time dependencies. What I mean by that is earlier when we saw these examples of when the stickings change with regard to context, we can see that it really matters what comes before and what comes after any individual prediction of a sticking. And so we want to capture, especially within music, which is so kind of motivic and uses repeated ideas throughout our work, we want to be able to capture these repetitions over time as at the start of a piece, at the end of a piece, even if there's something different in between. And to that end, we ended up using a model called a long short-term memory neural network, which is a recurrent neural net. It's a neural net that uses time series data and tries to preserve a long-term state to capture some of these long-term time dependencies. Now, I'm aware that there's also other, I guess, more contemporary models available, things like generators, which are kind of, I guess, the next natural step, but aren't considered in this particular study. We compared this against a baseline model of a hidden Markov model, which was used by Nakamura in the piano fingering study. And this is a much simpler model, still supervised learning model in this case, that is predicting the next situation based on what came before, much like Michael's presentation earlier. So this is a baseline model that we compared to. So we've got two methods of encoding, and we've got two methods of developing the model, of model design. So when it comes to actually implementing all of this, of course, all machine learning begins with data. And especially for an instrument like the marimba, which has a relatively young history in the Western contemporary music sense, unlike things like piano or guitar, where you've got music all over the place, this is relatively niche and it's quite difficult to find data. So I turned to probably the densest source, a single source of data that would be feasible within this study, which was an exercise book by Lee Howard Stevens containing 590 transposable exercises. What that all boils down to is once you manually transcribe everything and you put it into all its different variations, it amounts to somewhere on the order of 842, sorry, once you include the variations, it goes to around 840 or so exercises. And once you do appropriate transpositions into different keys, accounting for the various kind of physical permutations that work or don't, that ends up being around 30,000 exercises. Ooh, that's exciting. Okay. So all of this was transcribed, encoded using the various methods, and then the models were built. Both the LSTM, long short-term memory, as well as hidden Markov models were built and trained. And perhaps now this is almost the least exciting part of the whole exercise, which is to see where it all goes. But before we talk about the results, I just want to also mention a couple of evaluation considerations that are really pertinent to a study in this field. So the first is an evaluation consideration where we can have multiple truth states, multiple ground truths. Now, we're very used to the idea, I think, that if you've got a certain input, there is an optimal solution. But in this case, that may not always hold true. And so we wanted to make sure that our models didn't penalize any particular input for predicting a different answer, which was equally valid, but that would mark it as wrong. In this case, I've got two examples. So a sticking called 1, 3, 2, 4, and a sticking called 1, 2, 3, 4. And let's suppose that they're equally valid. Now, if the model predicts, 1, 3, 2, 3, under one marking mechanism, it's a score of 75%. Under another, it's a score of 25%. And conventionally, perhaps this would get averaged out to a 50% result. But we don't want this, of course. We want to say that any sticking which is equally optimal should be treated as such. And so we wanted to make sure we could implement this as a statistical process within the models, which we did. One aspect that was harder to quantify is the qualitative evaluation. As I mentioned at the beginning, one of the real challenges with this is that some aspects, this being music, can be quantified, and some aspects are really difficult to quantify. And so as part of this study, we also did a qualitative evaluation. And for various reasons, the results were difficult to find conclusive, mainly attributed to the fact of experimental design limitation being that, this one, that the data as input were exercises, not necessarily inherently musical passages. And so in a qualitative analysis sense, it ended up being that a lot of the stickings ended up being judged from a fairly physical sense rather than a musical sense. But that's not to say that there weren't no examples. So we managed to get a little bit out of that, but I think there's certainly further work to be done in that area. A second data limitation was simply the lack of data. Now, we chose a source of data that was as dense as we could find, but even so, it's still, on the scale of big data, very, very small. And so we're hoping that this is a starting point rather than kind of a definitive looking data set. Okay, so on to some results. I've just highlighted, I guess, the most successful results in each in gold, but I can briefly explain what that means because it's just a page of numbers at the moment. So of the hidden Markov models, which were our baseline, a third order hidden Markov model was the most successful in this case. Oh, the top of the screen is blocking a little bit, but refer to the right-hand column, which is using the multiple ground truth evaluation method rather than the strict marking mechanism. So our third order hidden Markov models did pretty well, but our more computationally intensive long short-term memory networks were proving to be a little bit more efficient or a little bit better at predicting good stickings. And we found that those of size about 100 hidden layers were doing particularly well. And in this case, that our pitch vector encoding, that long vector one-hot encoded, seemed to be favorable over the shorter interval transition encoding, but at a much higher computational cost. So just to wrap up, I think the goal at the start of this was to develop some kind of program that would help us to put in notes and rhythms and predict stickings out for end users to be able to improve performance. And I think this project has produced just that. I think there's still a large number of limitations in the design and in the data especially that limit the application of this particular model being used in the real world. But I think it forms a first step into a data-driven exploration in this field, which doesn't as often receive this kind of attention. And I'm hoping that it might be a springboard for future work. So if nothing else, I hope this has been an interesting exploration of data science in a less common field. And yeah, I'm looking forward to taking some questions. So thank you.
Thank you for this interesting talk. I should have used those sticks, much more intimidating than the rest, to keep the speakers in line. Any questions from the floor? Yeah, shoot.
So you did say that you looked into, I guess, how efficient and quickly it was in the distance, but also you were measuring how to perform it musically and most expressively. How is that measured?
I think, yeah, that's a really, really good question. And I think in this particular, I can answer that maybe in two parts. In this particular study, we didn't have a quantitative metric for this kind of qualitative variable. So that was mostly achieved through the qualitative analysis. So getting various practitioners to play it and to rank the outcomes. So that was how we did it in this case. In other cases, what we can see is examples where existing professional players have gone through music and put in, I guess, their approach on what is a musical way to play a certain passage. And then that feeds into the training process. And that's where we want to see if we compared that output to one that was strictly designed or geared towards cost minimization or movement minimization. Are there differences there? And perhaps that's something that would be better measured in a quantitative sense.
There's also one question online from Lisa Thomason. This is a very interesting application of statistics. Sorry, I can't make the Kiwi accent. Do you play marimba yourself? And have you, a musical friend, had a chance to evaluate the predicted stickings?
Thanks, Lisa. No, that's a really good question. Yes, I play the instrument. That was one of the drivers for this. And yes, the qualitative evaluation that we conducted was hands-on in that sense. We got the results out when we put in certain inputs and tried to read them. And at various stages of this experiment, we got some really interesting results. Sometimes it was just saying, use one stick and play the whole thing with one stick, which I guess technically kind of works, but is, you know, very trivial. And in another sense, there were occasions where it was playing 3 notes at the same time and it said, use one stick. And it's like, great. There was also one situation where it said, use stick 5, and that really confused us. So
Programming error, yeah, this happens. In the interest of staying on time, okay, just because you are the conference.
I got the full rank. Thanks, Jay. Really fascinating. I'm a bit disappointed you didn't bring in a marimba to show us exactly. But it occurred to me that have you sort of a sort of sports science approach to this, where they have video capture and maybe even sensors and if physicality and like you can measure fatigue in the musician, and maybe that approach to, you know, adding some more knowledge into how this problem might be addressed.
yeah, I love it. I haven't considered it as a sports science thing, but actually at the moment we're developing, I guess, we're developing sticks where we've built motion sensors into the heads themselves and are trying to be able to track the motions. Not in this case, not so much for the motion data itself, but to more rapidly gather data as it's being played. But that would certainly be a great kind of further path on which to take this. So thank you. That's a great input.
A good suggestion, yes. And any other questions, please, then on Slack or during the break face-to-face, because now we are already a little bit over time, so went so well so far, but Xixing just has this pull and this. Yes, so while Xixing is hurrying up our next speaker, I realize that I can take a little bit more time with announcing speakers. So our next speaker will be Ryan from the Curtin University. I need it all the time because it's a long title. He will talk about conveyor belt ware forecasting through a Bayesian hierarchical modeling framework using functional data analysis and gamma processes. And we are not yet ready. Yeah? Good. All right, 5 minutes. Please.
Yep, thank you. So today I'm going to talk about decision-making under uncertainty, but more specifically about, sorry, it's sharing the whole screen. All good? Cool. Yeah, so more specifically about decisions about when to maintain overland conveyor belts in light of limited data and uncertainty in the degradation process. But first of all, like, what is an overland conveyor belt and who cares about them? There we go. So these are some overland conveyors on an iron ore mine in the Pilbara. And pretty much once the ore is being crushed, they transport the ore around the mine site, and then the only way of doing this And as you can see here, they're very long and there's no redundancy in the system. So engineers try to ensure that there's no unexpected failures during a planned period of operation. And one of the biggest and most critical components on the conveyor that can fail is the actual belt itself. So the structural integrity of the belt comes from the carcass, which is made up of steel cords. And this carcass, to protect it, is sandwiched between 2 layers of rubber. And then just over time, the top layer of rubber that comes into contact with the ore slowly wears away. So to protect against the carcass being damaged by the ore, when the belt gets stopped for some reason or another, engineers take ultrasonic thickness measurements across the width of the belt to get a picture of the wear profile at that time. And then they monitor this wear, the evolution of this wear profile, to try and determine when the rubber will become, or there'll be too much wear and there's a risk of damaging the carcass. So that might be at like 15 millimeters of wear here. So to help them do this, we've developed a Bayesian hierarchical model. And rather than specifying a large complicated likelihood, we use a set of conditional models. So in the data model, we model the observation process, and then the process model describes the actual degradation process itself. And then in the parameter model, we're describing our uncertainty about the parameters or our priors. So for the data model, we take a functional interpretation of the data. So this is to say that the sets of ultrasonic thickness measurements at each time are noisy observations of some smooth underlying random function. And we assume that this random function can be described by a B-spline with a fixed set of basis functions. And this allows us to model the evolution of the curve through time by modeling the coefficients of that spline, which is the y's. And this is exactly what we do in the process model. So we use a gamma process to describe the evolution of the coefficients. And basically in a gamma process, we're saying that the increase of each of the coefficients from one time to the next come from a gamma distribution, where the shape parameter of that distribution depends on the amount of tons that go across, or tons of iron ore that go across the conveyor belt between this time and the next. And using a stochastic process like the gamma process means that we can model the heterogeneity in the wear rate that can arise from things like environmental conditions or variations in the ore body. So after we've defined any prior information that we have in the priors, we then implement this model in STAN to use Hamiltonian Monte Carlo to sample from the posterior distribution. And then once we've obtained these samples, we can produce a forecast for the engineer. And we do this by first defining a prediction horizon, which would be T forecast here. And then we sample the jumps in the coefficients using the posterior samples of the parameters. And then because it's a Markov process, we just add these jumps to the most recent set of coefficients. And then we kind of map this back through the data model onto the data space to produce a distribution of curves at that time, which is what you can see down the bottom here for week 24. So the black line is our kind of median curve, and then the ribbons are our uncertainty around that prediction. And you can see that it's highly likely in week 24 that the threshold will have been breached, and the black dots are our truth at that time, which were withheld during model fitting. So it has indeed breached that. And so using this method, an engineer can say, well, I've got a shutdown in week 18 and I've got a shutdown in week 24, both of which I can change the belt in. What will the curve look like at this time and how likely is it to have failed? And then they can base the decision around that. Cool, thank you.
So 5-minute talk was without question, but of course, put questions into Slack or whoever's here can jump on Ryan and ask him questions. And I hand over to Lucy again to say how the program is continuing.
Thank you very much, Berwin, and thanks to the 3 speakers as well. We'll take a short break now and we'll come back on the hour, midday Perth time. Thank you.